10.4 notes, polar coordinates graphs. This is page 3. And we're going to take a look at example 5, circles. And so this page is nothing but circles. We're going to kind of breeze through this fairly quickly, looking for patterns and at the patterns, so you know when you see an equation which ones are pretty straightforward. So A says we've got a center at the pole, and these equations will look like R equals A, where A is some number. So R equals 2, think about what that's telling us. R equals 2. R is the distance from that pole, or the radius. So this is a circle that has a radius of 2. And so that's all this means radius is 2. And so, I mean, anywhere on this circle, I got a radius of 2. Apparently my graph is not square. Okay. Done. If R is 5, then we know it's the circle with radius 1, 2, 3, 4, 5. And so we are just looking at, yeah, that circle. Nice and circular. B, the second set of circles we're going to look at are going to be tangent to the pole with the center at 0A. So halfway between the 0 or the pole and your maximum. And so this is the kind of circle we just looked at on page 2. This is going to reflect across that vertical axis, that line theta equals pi over 2. And I think the book has it this way. R equals A sine theta, where the center is at 0A over 2, means the exact same thing. I've always kind of liked this version better. It seems to be a little easier for me to remember. So here's our example. R equals what? 4 sine theta. That means I have a center at 0, 2. So here's my 0, 0. Here's my center. Here's my 4. And then I am going to draw that circle. Awesome. That does not look like a circle. Draw that circle that goes through those 2 points and looks like a circle. It's not going to let me make it bigger. Move it a little bit. There we go. Okay. If we have this, oh no, R equals negative 6 sine theta, think about where that puts our center. All right, so from that pole down 1, 2, 3, there's my center. So 6, I have 0, and I just end up with the circle that hits both of those points. Again, we're not looking for exacts necessarily. We want the general shape. You know, as we saw on page 2, how to plot that R equals 1.73. No way to get that exactly. Point is, we know that this should be a circle, and so we set this up so our graph looks like a circle. Last form of a circle we have are those circles that are tangent to the pole with the center at A0, and those are going to look like R equals 2A cosine theta. So here's our first example, R equals 2 cosine theta, which means my center is half of 2 is 1, so I have a center at 1 theta. I know that this goes out to 2, and I'm looking for the circle. It goes through the pole and 2, 2, and has a center at 1, 0. And so if we want a circle that's going the other direction, r equals, what can we use, -4 cosine theta? We know our center is at -2, 0. So here's my pole, here's my -2, here's my -4, and now I have a circle that hits -4, 0, and 0, 0, and is centered at, why does that one disappear? Here we go. Centered at -2, 0. Use your imagination. Circle drawing tool works well to a point. Okay, so these are the 3 forms of the circle that you'll see. R equals sum A. Keep in mind R is our radius. We'll get R equals 2A sine theta. Think back to the unit circle. That sine is our vertical displacement. So it makes sense that this is a circle that is centered along that vertical axis. And then for C, we've got something times cosine theta. Cosine is our horizontal displacement. When we see that 2A cosine theta, we've got a circle that reflects across that horizontal axis.